Great. I'm David. I'm from Tenfifty, and I'm gonna continue on the same topic that Marcus told us about and talk about what happens when you don't have that much data. And what I'm going to tell you about is Bayesian belief networks. And we're currently doing a project with this together with a customer. But the customer wants to do their own release of their product later this year. So I'm not allowed to tell you the name of the customer, and I'm not allowed to tell you exactly what we're doing. It's going to be great fun anyway, but I can't tell you those things. I can say that it's in healthcare. So I'm going to start by just explaining what is a Bayesian belief network. I'm going to give you some live examples of how they're used and what happens when you calculate and what sort of conclusions you can draw. I'm gonna talk about known application areas where people use it a lot. And since Bayesian belief networks in themselves is just statistics, and this is a machine learning meetup, I'm gonna talk about learning. How can we make them learn from data? Because we start by making them, well, you can't start with data, but you can start also with an expert that tells you this is what I believe. And this is how I think that things are connected. And then after that, when data starts coming in, you want to learn from that. You want to know where the expert were wrong. So I'm going to talk a bit about learning, and then we're going to draw some conclusions. So how many people here have a solid understanding of what a Bayesian belief network is? Don't be shy. So, yeah, okay. A vague understanding. Okay, good. Then I can show this without being embarrassed. So what is a belief network? A belief network is a graph that holds a belief about something. In this case, it shows the connections between different observable facts. So in this example, we have difficulty, which is all these nodes. In the live examples I'm going to show you later, we're going to have continuous nodes as well, so continuous features. But in this simplified case, we just have Boolean or binary nodes. So we have difficulty, we have grades, or in this case, not binary, but categorical at least. And we have a letter of recommendation and SAT score and intelligence. So we know that intelligence will affect what you get on the SATs, on your general school tests, and it will affect what grade you get. And you know that your grade will affect your letter of recommendation. And so this is a real simple graph of causality. And in this graph, to make it a Bayesian belief network, I have to tell it two things. I have to say what my prior is, and I have to tell you, which is just, before I know anything, what is the statistics of this? How many would be smart and how many would be dumb according to some cutoff they use here? It isn't important, but we need our priors, just the prior guess before we know anything. And then we need these arrows, which is the probability given, or the posterior then, the probability of the grade given that we don't know anything except what the intelligence is, or we don't know anything except what the difficulty is, or the letter given that we only know the grade. So the prior is we don't know anything, and this arrow is the only thing I know is this thing above me. What happens then? And given those things, I can observe any of these nodes, and I can go in any direction and say, if I only know this thing, then what is the probability, or what's the distribution on all the other nodes? What do I think of all the other nodes? And the reason we call them Bayesian belief networks is because we use this, the Bayesian update formula, which tells us that the probability for a node A, for something A, given a node B, the parent above it, can be explained by knowing the reverse direction and these priors. So we gave the priors, and we gave the arrows in one direction. So these are the priors, PA and PB. And then we give the arrows, let's say PA given B. But this formula gives us the possibility to walk in any way in this network. So we can also, if we go back, we can go backwards in this arrow as well, since we know that PBA is PAB times PB divided by PA. So it's very simple to know if we have this arrow, we know the reversed arrow. And it's extra simple when you only use these categorical variables or discrete variables. When you come into continuous variables, it gets messier, but not that much messier. So this is an actual program. This is our software. This is a front end for building belief networks. And of course we have a back end for doing calculations. And this is in Swedish, but I know most of you understand Swedish, and it doesn't really matter. So what we're going to do here today is that we're going to solve a murder case. Mrs. Astor, the wealthy widow, has been murdered. And we want to find out is if the butler did it or if a burglar did it. And with my long experience in criminology, I have encoded my expert knowledge on how different things affect each other, and by observing things, we're going to draw conclusions. So we all know that the butler did it, but try not to know that. So the thing with the ring around it here, those are conclusions. Those are things that I can't observe and I can't ask about. These are things that I want to know. And the purple thingies, these are things that I can observe or ask about, potentially things that are expensive or difficult to observe. Some observations are cheap, but some observations are very expensive. Like if this were medical, doing an X-ray is sort of expensive. Doing other types of testing is much more expensive. While some testing, like just looking at somebody, is quite cheap. So I could, in these models, also know what sort of answers I could incorporate. What is expensive to ask about or observe, and what is not. And then I can find what question or what thing, given that they're all equally expensive to ask about, do I want to observe next? And this is also a way that you can do a chatbot from this knowledge network. If your chatbot is a domain expert in something with a complex causal relationship, like you want to do error, some sort of system analysis. I'm coming back to some real application areas for that. So these blue things, they are things caused by the circle things. So if a burglar did it, he may cause a broken window. Or if the butler did it, he may cost a butler glove found at the scene. And this orange thing, a bad neighborhood, that's what we call a risk factor. And that's something that will cause other things. So a risk factor is something that may cause a conclusion, may cause a burglar to do it. A bad neighborhood in this case, which is a continuous node. I'm coming back to that. And this is a circle. It doesn't have to be a circle. It could be any shape. I might add a node or a connection live for you later. So the difficult thing, or one of the things in getting an expert to encode knowledge such as this, is that reality works in this way. We know that a burglar causes a broken window. But when we reason the other way. We know that the window is broken, so we reason backwards towards a burglar probably did it. So they shouldn't add the knowledge from how do I reason, but add the knowledge from what causes what. So it's reverse from how a normal human being thinks. And that always messes stuff up unless there's someone there to clear it up. So here we have 5 nodes, 3 of them observable and 2 of them outcomes or diagnosis. We can start with looking at this node, the butler did it node. It has a prior. I can edit it by doing this. So the question here is, what is the prior probability given that we know that the murder has taken place, that the butler did it? And we know that it's usually the butler, so I'm giving it in this case, a 59% probability just prior to anything. Of course, the natural probability of a butler did it is much lower. If we don't know that a murder has taken place, it's extremely low, right? You can't just walking around accusing butlers of murdering things. You have to know that someone was killed. Otherwise, it's much, 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 much lower. But still, it's a number still. So this is the prior, given that we know that something has happened. And this something can be a murder, but it can also be a patient seeking a doctor or something being wrong with my nuclear power plant, which is also something where you use it. And so we know that the butler did it, that's a node. We say that broken window. Now, if we're gonna guess what's the probability given that the murder has taken place, that the window to Mrs. Astor's house is broken, then that might be hard to guess, right? An expert might know, but it's hard to guess. And if we guess stupidly that this number is low, it's 1%. So this is a log scale, so it's easy to give low numbers. Then we have a problem, because our other connections, we know that burglars tend to crush windows, and we know that burglars tend to be the murderers at a certain rate. So other information in the network can contradict this thing. So since we know that sometimes the murderer is a burglar, and we know that burglars crush windows, we know that given that there is a murder, the probability must be larger than that. And that's what this little number tells us. If that's larger than 1, we have a contradiction. And humans tend to contradict themselves. We don't have, if you ask an expert, a criminologist or detective, to add all this information, all this knowledge, which is actually how we work, then they will tend to be contradictory. So we have to resolve these contradictions in some way. But it's completely okay. So this is one way of resolving them, just telling the person you're doing something stupid. But it is completely okay for this number to be below 1. Because if it's below 1, then we know that, sorry, my voice. then we know that there might be another explanation for broken windows than just the burglar and the butler. So I might not have the full knowledge of everything in my graph. In fact, I have to assume that I don't. So there may be other reasons for windows breaking, and those other reasons are encoded in this. The lower this is from 1, the more there are of other knowledge that I haven't encoded yet, or may never do. So that's also important for a human to look at. So here we say that the broken window has this prior. I'm going to show you one last prior. So this is the bad neighborhood prior. And this is a continuous node. And maybe I should edit it. So this is a continuous node where I say that given a scale from 1 to 10, you're not going to see that but it says 1 to 10 here. What's the shape of the prior? So most neighborhoods are in the middle. They are 5s on some scale, and and I've told you that it's sort of normal distributed, but with a fat tail. And I believe that quite a lot will be 10s and 0s as well, given that I know nothing else about anything. So there are, I could of course, instead of just drawing this, which we have done, we put out points and we draw it, I could use ready distributions. I could use a normal distribution, or I could use whatever, but as it turns out, when we're talking about this Bayesian updating formula, I want to follow the arrows one way, and I want to follow the arrows the other way. I want to be able to walk around. I want the information to be able to flow around in this network. Then I have to know, so this is the probability density function that I give here. What's the relative probability for each point? And if we sum this up, so if we sum this up, we get the monotonous function called the cumulative distribution function, the CDF. And since it's monotonous, I can invert it. So I can go from the y-axis to the x-axis as well. And that's called the inverted cumulative distribution function. But the problem is that our standard probability functions, they don't have a closed form. Even the normal distribution doesn't have a closed form for its inverted cumulative distribution function. So this is where, if you look at libraries for this, open source Python libraries for Bayesian belief networks, they usually skip continuous nodes because it's hard to specify distributions where we can invert them. It's hard analytically. But we take a very simple shortcut. We just divide this continuous function into 100 small categorical functions. So by discretizing the problem and using torch, which will let us use 100 points just almost as quickly as we use 1 point, we cheat and we pretend that this, whichever continuous function it is actually 100 discrete points. And now we have our nodes, and we have links between the nodes. So given that a burglar did it, what's the probability that the window is broken? So probability of broken window given a burglar did it. And I, from my long experience, say that it's 80%. And of course, the butler might be smart and also break the window, but that only happens in 10% of the cases that the butler tries to make it look like a burglar. And given all this information, and given that we haven't observed anything what's the most probable, given that I have no information at all? Well, I've already told you by the priors, it's a 59% chance that the butler did it and a 50% chance that the burglar did it. And the most valuable node to observe is broken window. That's the one that we calculate would give us the most. If we know this, then it gives us a lot of information to sort of differentiate between the butler and the burglar. If I'm going into this network again and saying, well, a lot of butlers, they're smart. So they tend to break the windows as well. So in 60% of the cases when a butler did it, they also broke the window. If I recalculate now, hopefully I haven't tried this, but I have great confidence in math, then hopefully this number, this broken window number, will go down. It will be less important to observe because it won't differentiate so well. And it did go down. God, I'm happy. But still, it's an important question to get right. And in this network, we've also said that a bad neighborhood affects two things: butler glove found at the scene and a burglar did it. So if I can go here and I can observe, I can choose to observe my first thing. I know the neighborhood and I know that this is a bad neighborhood. So there will be many burglars, maybe. So this is the prior, but now we know that the posterior, we know that's a bad neighborhood. The question disappears from the things it wants to observe, and suddenly it thinks that maybe a burglar did it. Because a bad neighborhood, then it's more reasonable that the burglar did it. But we can also see that it didn't affect the probability that the butler did it. And that's because there's something wrong with our network. Or something, we haven't encoded one critical piece of information in this network. And it is, we've given all these priors, given that we know that the murder took place. But we want to explain away use something called explaining away. So there's a reason that we're looking at this, and that could also be a node. And if we know that the burglar did it, then we also know, we can reason that a butler didn't do it. I mean, maybe both did it. In some cases, if it's a disease or you have a bug in your code, you can have two bugs. Or there could be two killers. But if you have found one, then the probability of there being another killer should be the prior of the population. So it should be much lower. It's still possible that the butler did it, also wanted to do it, but that's just the population prior. It's not the prior given that the murder has happened. So in our actual system, we have a hidden supernode that just tells us that someone came and asked you. What's the prior for this, given that someone came and asked you, and what's the prior, just the population general prior. And when you add that, then as soon as a burglar did it starts to rise, the probability of other reasons starts to get lower.
Is it still possible to end up in a situation where they sum up to something more than one?
Yeah, of course. The sums of the probabilities are not, doesn't at all have to be one, since there could be more than one diagnosis or outcome. There could be two things, but it should not be much above one. That would be strange.
But technically, the butler could, get together with the burglar.
Yeah.
Let's make some money.
Or independently. What I'm talking about is mostly the independent. The butler could independently want to kill Mrs. Astor the same night. And that's why it can be higher than one. Or we can independently have 2 bugs in our code or 2 diseases. But so we can't rule out just because we found one bug, one reason for our program crashing. We can't rule out that there are other reasons that it crashes as well. But those probabilities get much lower. In my case, very low, I want to say.
If the butler finds a broken window and sees its opportunity to kill.
Yes, so then we have to start adding new arrows of causality. There can be, and if we think about this in general, what we have here is a classification task. If we had a lot of data of all these murders, then we could use just a normal classification, like a neural network or a booster tree or something, and we get this multi-dimensional area or surface of, given these 3 dimensions, these observable dimensions, what is the frequencies of the other things. But we're making it much simpler, and we're doing that for 2 reasons, which I'm getting back to.
I mean, if something is correlated directly, how would you control that?
Sorry, if something is correlated.
I mean, if it was that the butler murdered the burglar. Or the
What?
If something is correlated directly within the network, if I know that something is correlated directly by the prior, I mean, that
I can draw arrows. If they are correlated, I draw arrows between them. So I add connections. All the correlations are these links, these connections. So I say, well, a bad neighborhood will also increase the probability of broken windows in general. So then I can add a new link and say, does that answer your question? So I can ask.
but it's fine.
Yeah, okay. So I can add nodes for those type of things to explain causality. There's also some details which I'm not getting into. A node could be an or an and node. So I can say that a node for a node to happen, for something to happen, all these things have to be true. Or I can say for a murder to happen, then it's or any of these person, this person or this person or this person must kill me. That's enough for it to be a murder. But sometimes it has to be an and, where I say that must happen and this must happen and this must be true. So I can add different types of, but it's still very limited, and the limitation is the point. I can't add any type of connection, and I can't describe any type of surface. These are all linear connections, and they are quite simple. They're usually not correlated, which gives us a low dimension to work with, which means that we can use data. For each data point that we can get in, we can get so much more from the data point than if we have lots of dimensions to optimize in. So all these areas are areas where there's a company, I think they're from Norway, that is called Norsys, which makes sort of a program for this for non-statistical people, and they list client in all these areas. For example, you can see here that the Swedish Defense Research Agency use belief networks, Swedish Radiation Safety Authority, and it's used to model the environment, usually local environment. What happens if this lake gets more acidic, what happens over here, and what's the causality given how nature is connected. And it's used in, we use it in medical, and obviously it's often used in science where you don't always have that many data points. And an early application was in mining, where it's very expensive to observe something. If you want to know where should I drill, then it's very expensive to drill, it's very expensive to test. So you need these causality networks on how certain geology affects something else and how a water reservoir somewhere would possibly deposit something somewhere else, to make sure that you're observing as few things as possible. And now we get to the learning part. So there are no labels here, and I'm sure this is self-explanatory, so I'll let you look at it. No, so actually this is supposed to be reality. Reality affects our expert, our teacher, the one who adds these nodes and these probabilities. And that person then makes a sort of correct network. When you make it, you don't have a notion of this person being wrong per default. So if data comes in afterwards that looks very low probability, so if strange data comes in, things that your network says shouldn't happen very often, if it starts happening often, then something was wrong with this connection. So what we can do is that we can say that reality causes our network. So we have a meta model where we say that this is the network that someone has given as output, but it might not be the true network. There are two types of errors. There are things where you're slightly wrong, let's call it noise, which we can say is Gaussian, and there's cases where you just put in the wrong value, which would be another type of error. And we can say that if enough data comes in, then it might be more plausible. The lowest probability of the entire network might be to start adjusting the weights in the network, or not the weights, but the probabilities or even the connections. So we can compile a new network once data starts coming in and saying, well, given that I think that it's this probable that this person is wrong, how much should I move each probability or each connection, each prior, so that I get the most probable solution, the most probable compromise between this person being wrong and that sometimes data comes in which isn't that probable. And the lower part here, that's the thing that happens all the time. That's the user entering information. So if it's a chatbot and you ask the user things, then the user will answer, and the user might be wrong, the user might be lying, and the user might be misunderstanding. So what we're currently experimenting with is having a node in our network, the user or reality, which affects the node that we want to observe. So we say that I don't know if a person has red eyes, to make a medical point. Perhaps they're lying, or perhaps they misunderstood the question. All I know is that they said that they had red eyes, which is highly correlated to them having red eyes. But if they start saying other things which contradict this, then I can maybe ask them again in another way. Are you sure that you understood the question? Or I can start dismissing that answer as spurious or wrong. So this meta model of the network gives us a way of knowing both when our network should be changed and also when the input from the user should be dismissed, or if I should re-ask. Maybe I have several ways of asking the same question. So that's where the learning comes in. it's gradual. So the trade-off from this, there are good points and there are bad points to using this. You get gradual learning from the first data point. You start with an expert knowledge. You can actually start with data and infer your network from that, but I won't get into that. But you get to incorporate expert knowledge, and from the first data point, you sort of get to learn what the real joint distribution, which we call it, looks like, the real predictive model. And another positive thing is that I get to have true uncertainty in both the input. Someone can say that I think I have red eyes. Maybe that they don't understand the question or don't have a mirror or whatever. So I can have that in my model as well. I can say that given that they say that they think they have it, it's just an 80% chance that they have red eyes. And I get true uncertainty in the output, in the conclusions as well. And we get something very neat. We get explainability in human concepts. I can explain why. That's often very important for a model, right? My model can say, because this and this and this, I think that this. But if this observed thing were more normal, if this thing which you've told me, which you observed, were more like the prior, then I wouldn't think this. So that's basically how you answer a why question. You find the node which you have observed, which if you didn't observe it, would change the answer the most. And you say, because of this, I think this thing over here. So that's a good way of explaining to an expert why you think something. But the exact solution to this is NP hard and very, very expensive. So you do approximate solutions. And inferring the topology, if you don't have an expert, but you have some data, you have a few thousand data points, and you want to guess the causal topology, that's even harder. You can do it, but it's really expensive. And of course, we end up with this highly simplified joint distribution. So our model is very simple compared to a neural network or boosted trees, because it's much more linear, because we need to have explainability to humans, because a human gives us explainability, and because we want to work with few data points. And the library support is surprisingly poor. So this is just quickly, this is a real network. This is something, I'm not going to show you what each label is, but what we have here is risk factors, the orange thingies. We have the purple thingies, which are conclusions. We have the blue thingies, which is what our conclusions leads to, the symptoms. And we have the orange thing in the middle, which we didn't have in the last thing, which is the action. It is, given that I think that this thing has happened, what action should I take? So we have nodes from given various outcomes. What do I think I should do? And which helps us. If I think that's a 50% chance that there's that this thing has happened, a 50% chance that this thing has happened, then but the action should be the same thing, then they sort of build up towards the same action, if it's the action that I'm interested in. So, in conclusion, this is the last slide. Belief networks are widely used, but they are less used in the machine learning community. And part of that, I would say, is because the large companies like Google and Facebook, they suck up all the AI researchers. And of course, large companies have a lot of data. So they're interested in things that concerns a lot of data. And that's nice because they share these results with the rest of us, and it's great because it brings the field forward. But it also gives us a bias towards large data. It gives a bias because that's what the large companies want, and the large companies are the one with the most public researchers. And so that's also what the universities will tend to look at. Of course, some will look at small data and how you do transfer learning from big data to small data. But given how useful it is for a normal company, it's way, way, way underused with libraries and what sort of exposure it gets. Not only belief networks, but other low data things as well. So these would be suitable for simulations, since you get uncertainty out and uncertainty in. They are suitable for all types of system diagnosis. For nuclear power plants, as I mentioned, for something large and technical like your own software system that runs in deployment, for people, for cars, they're used for all these scenarios, and then can be used for complex dialogue. If someone wants to ask an expert something, then that expert can be a belief network, which can choose the next thing to ask the user back, and so forth. So you don't get these hard-coded chatbot trees, which are so frustrating. Yeah, thank you. Do you have any questions?
In the almost last network
Yeah.
description, the orange dot, is that the state or is it the action?
The orange dot in the middle, that's the action. So it's a categorical node with different types of actions. And everything,
Different type of action.
yes, so it's categorical. There are different types of actions which are hidden inside that node. So different beliefs will lead to different probabilities of different actions. So you can say, I'm 90% sure that you should take this action given what I believe about the world.
And is that correlated to the link you take into the...
Yes, so I say that given that I know that something, or given that I believe that your radiator is broken, you should order a new radiator, or you should go to your repair shop. And a lot of errors would be the action is that you should go to your repair shop, but a lot of actions might be you shouldn't do anything at all because it will clear up itself, or you should throw away the car because this will be too expensive. So if you have these three options, wait, go to the repair shop and just throw the car away, then different beliefs about what's wrong with the car will lead to different actions. So I can, in the end, I get an action distribution saying I'm 60% sure, and I can keep asking you questions and you can keep answering them. They might be expensive to answer because you have to do some tests, or they can be cheap, until you're certain enough of which action I should take. I might not be certain of what's wrong with it because that's not my purpose. I just want to know what should I do.
How does it?
Okay, you first.
Let's say you have like a set of symptoms which give low blood pressure, and you have another set of symptoms that give high blood pressure, and you have an observation that is, your average blood pressure. How hard it is to sort of code in this sort of more complexities into the system?
That would not be so hard, because you wouldn't divide it into low and high blood pressure, but you would have a continuous node saying what is your blood pressure, and then you would have risk factors leading to high blood pressure, such as not exercising or whatever, and you would say that, well, if this is true, then the posterior should look like this. This is the curve given if this is true, and this is the curve if it's not true. So if I can make the assumption that all risk factors are independent, which I sort of can, then I can say it's quite easy, because I make them independent and it works. Yeah.
Why is there a need for a special type of action node?
Because there's no need for it, but if all you're interested in is the action, then you don't need to, then you should ask the question or make the observation which leads you to an action with the highest probability, and not to a diagnosis.
But, it's just like, how does a statement, you need to go to the car repair shop,
Yeah.
differ from a statement, I believe you need to go to the current version in that terms?
No.
Is it just the color of the node, or is there some sort of functional difference between the two?
Well, so I'll try to explain once more. Since the target is what should I do, and these diagnoses, they affect my action, then I don't have to know exactly what's wrong with your car. I only need to know that there's something serious enough wrong with your car that I know that you should throw it away, or whatever.
Right.
And that says that I can stop asking questions earlier, and it also says which sort of questions. I should ask questions which divide the car into serious or non-serious, rather than questions which makes me very sure about what is wrong with your car.
Okay, so this seems like a domain distinction rather than a distinction within the Bayesian network.
Yes, so of course it is. It's not mathematical distinction at all. Yeah.
Do you use regression anything to find the correlations or the priors?
No, we sometimes look up the priors because sometimes they are in literature, but we use an expert to tell us the prior, and then we use the learning thing that I told you to say, now we've gotten enough data to start saying that we think the expert was wrong, so we should start moving the priors into the most probable state, the most low energy state, or what you want to call it, the most probable state, given that an expert has said it, but the data contradicts the expert. Yeah.
But in Bayesian beliefs networks, I thought that you needed directed acyclic graphs. If you go back to a few...
Yeah, this is a cyclic. It just looks like a cycle because there are arrows in it.
Because you had a few there.
Right, I can go to this easy one if you want.
That you had the last.
Okay, then I'll go to that one.
There it seems like you had a lot of. That must be cyclic, isn't it?
Well, I am allowed to have cycles, but I don't think this is cyclic because there are arrows here, which you don't see. Yeah, so all these connections are directed. So you say that this causes this thing, and you don't see these arrows here.
Okay.
And that makes it usually not cyclical, but it can be, yeah.
But there is some point, right, that it does make it harder.
Yeah.
So it's allowed, it's still a Bayesian network.
Yeah.
It does make things more difficult.
It makes it harder to give an approximate solution to it. So you usually pretend that you don't have loops, even if you do. But there's something called loopy belief propagation which allows for it. And yeah. Yeah, so great questions, everyone. I'm sure I've gone way over time, but thank you. And we're hiring at Tenfifty, so if you like Python and fun and this sort of thing, come to me or to Marcus. Go to Marcus if you want intelligent conversation, because he's the one that has actually programmed most of this. Yeah, thank you.